All right. The first couple of problems at the top of the page kind of tie into what we're going to see today. We're going to see some problems and use some things that we've used throughout the semester and throughout last semester to kind of bring in some of the things that we need for today. So we're gonna prove that triangles are similar, like we've been doing the last couple of days, but now we're gonna prove it by different ways. And so today we have one theorem we're gonna use. Tomorrow we're gonna add some more to it. But first of all, as I look at these two triangles, I want to find angle x, right? Let's say I covered up this top angle right up here. What would I need to do to find the third angle in that bottom triangle? What do we know about a triangle? 180 degrees, right? And what's the angle measure here? 90. Here's 34, right? So these two we know. We're trying to find the third. There's only three angles in a triangle. So 180 minus 90 minus 34 would give us what? 56. Okay, so this angle here is 56 degrees. Okay, and then you might say, well, we're trying to find x. We are, but what do I know about x and 56? Vertical angles, right? They're directly across one another, where the two triangles meet. And so here we know that they're vertical, and we know that vertical angles are always congruent. So x is 56. Okay, as I look at the second picture, things that we've noticed about the picture that are really, really important to help us find what we need. First of all, we see these two arrows. That's an extremely important piece of information. Because those two arrows are there, what's that tell me about those two lines? They're parallel, okay? And here's what we've talked about before. Because we have parallel lines, then we can form all kinds of different angles with those parallel lines. For instance, what would I say about these two angles here? They're corresponding. And we know that if one is 58, then the other one is 58. Same thing would be true down here. If this one's 32, then this one's 32. Because this would be a transversal, and these two would be also corresponding angles. So we actually know both of those. And it really doesn't matter what picture you draw here, because both triangles are essentially the same thing. But if I were to draw a triangle that has angles of 58 and 32, and I want to find x and this top corner up here, then same thing as we did on the last one. We know there's 180 in a triangle, so I can do 180 minus 58 minus 32. And what's that leave me for x? 90 degrees. Okay. And there is no angle marking here, so as we look at it, does it look 90? I mean, it's kind of hard to tell. We probably wouldn't have looked at that immediately and say, oh yeah, that's 90. But based on the information we're given, we have to say that it's 90. Okay, so you're going to see some things like that today. And so what I'm trying to show you is that some of the things that we've done, and it's been a while since we've talked about some of those things, but we've talked about them a lot throughout the year so far. So those are things that are still going to get tied in to what we're doing here. Okay? All right, so the theorem that we're going to do today is what we call the angle-angle similarity theorem. And you might remember back when we did congruency, we used letters rather than writing out angle-angle. Back when we did congruency, we had side, 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 angle, side. We had all those different theorems, right? We had 5 different ways of proving congruency back in the first semester. But this is different today. When we were doing congruency, we said these two triangles were congruent, which means they're the exact same shape, same size, everything about them is the same. These are theorems for similarity, which means the two triangles, they are the same shape, but not necessarily the same size. But they are proportional to one another, okay? And we've talked about this a lot in the first couple of lessons of Chapter 8. But if two triangles are similar, or any two figures are similar, their sides are proportional, their angles are congruent. But what we're going to prove today is we don't necessarily have to be given any information about the sides, As I look at these two triangles, I don't know the side length of them, but I can prove that they're similar. And all we need to have is two angles. If we have two angles that are congruent, then these two triangles are similar, okay? But you got to really understand the difference between congruent and similar. Congruent means exactly the same measure. Similar means proportional. The angles are congruent, which makes the triangles proportional or similar, okay? Today, we're going to spend a lot of time talking about the similarity statement. Yesterday we saw a little bit, and I told you that it was extremely important. One or two of the problems on Big Ideas yesterday had pictures of two figures, but the figures were like rotated, okay? So the bottom doesn't always match up with the bottom. And I had a lot of people ask me questions about those because they're like, well, the two bottoms don't set up to make this ratio. That's because the two bottoms didn't match up with one another. So you have to pay attention to what goes with what. And we'll talk a lot about that again today. But today we're only talking about triangles. We're not looking at quadrilaterals or any other figure. The angle-angle similarity theorem only works for triangles, not for any other figures. The other difference that you'll notice here, when we did congruency back in the first semester, this had an equal to underneath the tilde sign. This is just the tilde sign. So that means similar to, okay? Whenever, and we talked about that, we've seen it already, but when I see this symbol means similar. And that's going to be the symbol that we're going to use a lot in this chapter. All right, so going down here. As we look at these two triangles, the first thing that we notice is we don't have any side lengths. And today that's going to be the case on a lot of problems that you do. You're not going to have any side lengths given to you. We want to know, is there enough information to determine if these triangles are similar? And if so, then we want to write the similarity statement, okay? So all we need for today, there's only one theorem that we're doing today, and that is angle-angle. And that means two angles must be congruent, okay? This one is 64, this one is 90. This one is 90, and this one's 26. So some people might look at that and say, nope, 26 and 64 aren't the same. But what we have to do here is we have to find the third angle, okay? To find the third angle, we know each of these has to add up to be 180 separately, right? So what would the measure of angle B, or sorry, E have to be? How would I get it? How would I get angle E? 26 plus 90 and then subtract it from 180, right? So 180 minus 90 minus 26. What's that leave me? $90 minus 26? 64, okay? So right now, can I go ahead and prove that these two triangles are similar? Yeah. I got a 90-degree angle. I got a 64-degree angle. I could go ahead and prove that K is 26 as well, but we only need two angles, right? And as long as I have two angles, then I would say, yes, these are similar by the angle-angle similarity theorem. And then it says to write a similarity statement. And that's why I kind of talked about that up above. The first triangle, you can write it any way you want to, okay? You can call it EDF, FDE, DFE. I don't care the order that you put the first triangle in. And we talked about that with congruency way back when. A lot of different ways that you can write that. But now, when I write the second one, it has to match up with the first one.
Where did you get the F from?
EDC, you mean? Yeah. Thank you, Hannah. I knew I'd seen an F somewhere. It just wasn't there. Or maybe I was just going alphabetical, right? Thank you. So since I listed E first, E is the 64-degree angle, so what has to be first in the second one? Okay. And then D is a 90-degree angle, so it's got to match up with G, and then C has got to match up with K. Okay. But I can't stress enough, order matters. You can't just put these letters in any old order you want to. The first one I can, but the second one has to match with the first one. Extremely important. Okay, this kind of goes back to the first set of problems that we did where we found angles. If you wanted to, you could redraw these triangles. And sometimes I think that's kind of helpful. But I think a lot of times you could probably do it without redrawing it, so it's kind of up to you. If you see it better visually, redraw the triangles. The one thing we know right now is angle B is 52, angle C is 52. So right now we got one pair of angles that are congruent, right? But we need two. Are there any other angles here that are congruent? Okay, it's the same angle, right? And so what do we call that when the angle is exactly the same angle? When two things are exactly the same. They are congruent, but how come? Reflexive property, yeah. We're going to say angle A is congruent to angle A by the reflexive property. And I know it doesn't ask us to write a proof or anything out here, but we have to have some reasoning as to why. We can't just say angle A is congruent. Why do we know that? Okay. Now, here's the tricky part. I don't know the actual measure of angle A, right? I eventually could maybe get there, but we don't really care what the measure of it is. We're not really finding the measure of angle A. We're just trying to prove that these two triangles are congruent. And here's kind of why I like to draw the two triangles separately, because as I look at my two triangles here, I got two angles here, I got two angles here that are congruent. So we would say, yes, these are congruent because of angle-angle similarity. Or not congruent, but yes, they are similar because of angle-angle similarity. Okay, when I'd write my statement out here, the first triangle can be written any old way you want to. ABE, EBA, BEA, however you want to do it. But then we've got to match it up. So A is going to match with A, B is going to match with C, and finally E is going to match with D. That's my similarity statement. Okay, on part B, we got these two triangles. We've got arrows. Arrows, once again, tell me parallel lines, right? So if we have parallel lines, let's think about, like, if I had two parallel lines like that. What would I say about these two angles? Okay, those are alternate interior, right? We got parallel lines, and so what we're going to say here is that angle S is congruent to angle U. We could also say angle R is congruent to angle T. Alternate interior angles are congruent when we have parallel lines. We have parallel lines, so alternate interior angles are congruent. Hey, could I have used this angle right here? Why would these two angles right here be congruent? They're vertical angles, right? And so I could actually prove all three, but I don't necessarily need all three. Hey, if I needed to, I could get there, but we don't need to. Okay, 2 is enough. 2 is all we need to do today. So once again, we're going to say yes. These two are similar because of angle-angle similarity. We proved 2 angles are congruent, which makes them similar. So then my statement here, I'm going to say triangle SVR is similar to, and then once again, here's where you got to be careful. S is actually going to match with U. Sometimes people might look at this and think, oh, S and T are going to match up because they're both up top, right? S and U are the 2 that are congruent. Those are the 2 that have to match up with one another. So S is going to match with U, V is going to match with V, R is going to match with T. And that would be my similarity statement. Okay, as we look at these two, these are kind of multiple choice questions. We got to read the question carefully. Can I assume that corresponding sides and corresponding angles of any 2 triangles are congruent? Why or why not? Any 2 similar triangles. So if 2 triangles are similar, what's true about their angles? They do equal 180, okay, because they're triangles, okay? But what about like if I compared like angle A on this triangle and angle B on this triangle? If they're similar, what would be true about their 2 angles? If we look back up here, what did we say about, like, for instance, B and C? B and C are what? The same, they're congruent, right? So if we have 2 similar triangles, the angles are congruent, right? What about the sides? When we talk about these 2 triangles being similar, are AB and AC the same length? What does it mean to be similar? The sides have to be what? What's the word we used yesterday? I told you it was a really big word that we got to know. Proportional. Good. Okay? The sides have to be in proportional. They have to be in the same ratio. It's going to be like this triangle is 2 times bigger than this triangle, right? Or 3 times bigger, or whatever the ratio is. Okay? These 2 triangles are not the same size. They're the same shape, but they're not the same size. Okay? So if I said that this was 2, does that mean AC is 2? No. Okay? It's some kind of ratio. We don't know what that ratio is right now, but we know it's either bigger or smaller, but it's proportional. Okay? And so the key word in this statement down here is congruent. The angles are congruent, and that's what we're doing today. We're proving the angles are congruent, but are the sides congruent? No. Okay? So as you look at these statements, which one, we've already determined no, so which one's better, the first one or the second one? Are corresponding angles proportional? What did we just say about the angles? The angles are what? What do you think? Congruent, right? So the angles are not proportional, the angles are congruent, okay? So that one does not make sense. So the only one that makes sense is the second one, part B, or whatever you want to call it. It's not really labeled. The corresponding lengths are proportional, but not necessarily congruent. Sides have the same ratio, but they are not necessarily congruent. Okay, if I have 2 equilateral triangles, are they similar? So let's look at an example. Sometimes just looking at an example is big. Let's say this one has sides of 4 and this one has sides of 8. Okay, so first of all, are my sides proportional here? Are all the sides in the same ratio to one another? How much bigger is this triangle than this triangle? How much? Yeah. So, and when we talk about ratio, we want to talk about like a multiplying factor. So like 2 times bigger, right? To get from 4 to 8, it's 2 times bigger, or this is 2 times smaller, however you want to say it. But all of the sides are in the same ratio, 4 to 8, 4 to 8, 4 to 8, right? So all the sides are in the same ratio. Now, the angles are not marked here, but what do I know about the angles in an equilateral triangle? We got 3 angles, and if they're equilateral, what do we know about all 3 of them? They're all what? They're all congruent. They're all equal, right? They are all 60 degrees, right? They're all 60. So this one would be 60, 60, 60. So are all my angles congruent? Yeah. Are all my sides proportional? Yeah. Okay. So we would say each angle is always equal to 60. We already know it's equilateral because all the sides are the same, so it would be in the same ratio. Okay, this one, it says to use the transformations to prove that what we've got. Okay, are these 2 triangles similar? Do we know anything about the sides? Do we care about the sides today? Because our theorem that we're using today is what? Angle, angle. That's it, okay? Angle, angle means I do not need to know anything about the sides, guys, right? We don't care about the sides. All we care about is angles. Do I have 2 pairs of angles that are marked congruent? Yeah, that's all we care about, okay? And so here we know that angle P is congruent to angle S, and we know that angle T is congruent to angle Q. Therefore, triangle PQR is similar to. Okay, now we got to match it up. Okay, Xander, what is P gonna match with? S, okay. Okay. Q. Corey, what's Q going to match with? T. Good. Okay, and then we only got one left over, right? R's got to match with U. Order matters, though, okay? We can't just put that second triangle in any order that we want to. Okay, and I should say something like by angle similarity again here. I forgot to put that. All right, choose the statement to show the similarity of FGH and RQS. Okay, and as we look at this, F and S, so we're going to match up these 2 here, okay? So as we look at this, we want to look off of, and I know it's a little bit tricky, and because these are equilateral, they're all 3 the same, it really doesn't matter. But if I just went off of this right here, what's F going to match with? It's going to match with R, right? Don't look at the pictures, look at the statement. F and R are the 2 that are going to match up. So we want F and R, and we want G and Q to match up. So that would be this one right here. Look at the statement, match up. First to first, second to second, third to third. Okay? And so that's what we want to do there. Because this is equilateral, you probably could go and say, it really doesn't matter which one goes with which, but we're going to go off the statement that they told us to use. All right, this one down here. What I would recommend on this one is redrawing the picture. Sometimes I would say the picture you could probably do without. This one, I think you definitely want to see what's going on here. And what I'm going to do is I'm going to redraw these 2 so they look the same. Okay? I don't want to draw it like it's already drawn. C, D, F is my first one. I redrew it just like it was in the picture. Okay, and then it says compare it to DEF. Now, a couple of reasons why I did it. So what I did was I took this triangle and I just rotated it, okay? I want my 90-degree angles to be in the same spot. I know this one's 90. How do I know that the other angle F over here is 90? It's not marked. What do these two angles together make? They make a line, right? And so if this one's 90, what's the one right next to it have to be? Because a line makes how many degrees? 180, right? So these both have to be 90. So we know angle F is also 90. Doesn't have a marking right now, but we know it's 90. We know that E is 58. What would be the measure of angle D right here? Do we just go ahead and assume that it's 32 because this one down here is 32? No, we got to find it, right? And because we have a 90 and a 58 degree angle, we can find the third angle. So if I take 90 minus 58, what's that leave me? 32. Okay. So what we've now proven is CDF would be this angle right here. That would be 58 degrees. Okay, some of us are still having issues with, like, going off of the test last week. When I say DFE, I'm talking about this angle right here, okay? Follow the path of the letters. DFE, we're talking about the angle that's in the middle. So we're talking about the 90-degree angle here. Follow the letters, always the one in the middle. Okay, CDF is 58. Oh, sorry, they're not asking for an angle measure there. It's congruent to, so CDF, and here's why I like drawing the picture out. CDF is going to be congruent to DEF. CFD is going to be congruent to DFE. Okay, we're just following the path. If I have this redrawn, then it's really easy to see the path, right? If I tried to do it off of the original picture, probably going to be a little bit more difficult to do. Okay, and so once again, for today, it's going to be pretty easy because we only got one theorem. If we can't use that one theorem, then we can't do it, right? So once again, it's angle-angle similarity. All right, so two different questions here. First of all, we saw one like this already, okay? These are alternate interior, these are alternate interior, these are vertical. So we're saying that these two triangles are similar, right? But what if I tell you, now notice that I have a parallel symbol with a slash through it. What do you think that means when I put a slash through something? Not, okay? Not parallel, okay? This means not parallel. So if SR and TU are not parallel, so if I were to redraw this picture, and this time we don't know if they're parallel, what's the only angle that we know is congruent? Yeah, the vertical angles, right? If SR and TU are not parallel, then we don't know if we have vertical angle, or we don't know if we have alternate interior angles. So all we have is vertical. Is one pair of angles enough? Because what's the theorem say today? How many do we have to have? Got to have two. One pair is not enough. We need to have two pairs. Okay? So if those two lines are not parallel, we only have one pair of congruent angles. So we would say no. They're not similar. All right, we're going to see some problems like this the next couple of days. And I'm going to post a worksheet for you today that's going to have about, I think it's got like 5 questions on it. And one of the most important things I'm going to tell you, we're going to do a couple of them here. You have to draw yourself a picture and label it, okay? Without a picture, it can be really difficult to do. And so draw yourself a picture. And what we're doing here, we got this ride that casts a shadow that's 80 feet long. At the same time, a person standing nearby is 5 feet 5 inches tall. That casts a shadow 34 inches long. All right, so here's our picture. I'm going to draw it as two separate. You got the ride, and then you'll see my good artwork here. See why I'm a math teacher and not an art teacher. A great little stick person. We're going to fill in the information. So we got this ride. The ride, we do not know how tall the ride is. So that's my X. That's my unknown. Okay, the shadow of the ride is 80 feet long. Well, when I think of shadows, where do shadows always show up at? Well, they show up on the ground, right? So this is going to be the ground down here, 80 feet long. Okay, you don't see like a shadow is suspended in there. That'd be kind of creepy, I think. The person is 5 feet 5 inches tall. And their shadow is 34 inches. To make this easier, I think it's probably easier to change everything to the same unit, right? So that way we're not worrying about what's feet, what's inches, and all that. If everything's in inches or everything's in feet, it would be much easier to change to inches. How many inches are there in a foot? Okay, 12 inches in 1 foot. So this one down here is already in inches, right? This one's going to be really easy to convert because if there's 12 inches in 1 foot, if I have 80 feet, what am I going to have to do? Just multiply by 12. So 80 times 12 would be what? So 80 feet or 960 inches. Okay, the person is 5 feet 5. Okay, when you go to the doctor's office, they might tell you your height in inches and feet, right? But a lot of times they're just going to measure you and say you were 60 inches tall, right? And then you can do the conversion if you have to. But 5 feet 5, we're going to take 5 times 12, which is 60, plus 5 would be 65 inches. So this problem is going to be a whole lot easier if everything's in inches, okay? So if you don't know that conversion, you might want to write it down. You're going to need it, okay? 12 inches in a foot. Okay, now we're going to set up a proportion. And this is what we've talked about the last couple of days. When I set up a proportion, there's a lot of different ways for me to do this. There's more than one way to do it, but we have to be exact about how we do it. We have to go in the same order, okay? So you can go small to big, small to big. You can go big to small, big to small. I don't really care what order you go in, but you have to stay in the same order, okay? So in this case here, I'm just going to move left to right. I'm going to say 34 goes to 960. I'm only going to use the inches here. As 65 goes to X. The nice thing about going to inches here is we don't have to worry about decimals or fractions. So inches is going to be a little bit better way to work. Now we can cross multiply. So we're going to take 960 times 65 and then divide it by 34. Okay, what's that get us? Big number. 1835 point, what's the decimal after it? 3. Okay. All right, so this is in inches. But if you were looking at this ride, they're probably not going to say, how tall is this ride in inches? When you talk about something this tall, you're going to talk about how tall it is in feet. So what would I need to do to change this answer back into feet then? Divide by 12, okay? So leave that number in your calculator and then divide it by 12. So you're going to have to really pay attention today to how they're leaving the answer in big ideas. Are they leaving it in feet or inches? If it doesn't say, probably feet is going to be the way to go, but it should say most times what unit you're leaving it in. Okay, try drawing a picture for the second one here. That way you have a little bit of practice. Label it and try to figure it out. I'll do it while you guys do it. All right, the first thing I'm going to tell you here is this is angle, okay? And the reason why it's angle is because we're talking about this person standing upright. Okay, so we're assuming the person's standing upright. If you're going to get measured with your height, do you slunch over, right? Say, okay, go ahead and measure me, doctor, right? Probably go to your physical. You're probably going to get big and tall. Make sure you get as tall as you can be, right? So that's what we're going to imagine. We're going to try to get big and tall. We're going to try to get our height here. And then the angle that these two are forming with the sun or whatever is going to be the same measure, okay? So what we're trying to do here is we're trying to, like especially at the tower, we're trying to measure something that's otherwise difficult to measure, okay? We call that an indirect measurement. I'm not going to take a tape measure up to that tower and say, oh, this tower is 152 feet tall. Probably don't have a tape measure that has 152 feet, right? In most cases. So we're going to use other things. That's where kind of the geometry comes into play. We can use geometry to measure things that are otherwise difficult to measure. Maybe like the elevator downtown or something like that. Okay, then we can set up our proportion. There's lots of ways to set up this proportion. If you didn't set yours up exactly like this, that's okay. Maybe you put the child first, okay? And maybe you went x over 34 equals 52 over 65. The biggest thing is that when I cross multiply, these two things should be multiplied together, and we're dividing it by 65. No matter how you set it up, those are the numbers that are going to go together here. Okay, what do we get? Anybody type that in the calculator? Landon, did you type it in?
Yeah.
What'd you get?
I got 27.2.
Okay. So 27.2 inches, okay? And because they give me the other shadows in inches, it doesn't really say here how to leave it. I went ahead and changed this one to inches. If I needed to change it back to feet, then I once again could divide by 12 and get feet, okay? But I'll just leave it in inches for right now. Okay, on this one I'm not asking you to draw a picture, but just once again to kind of talk about how to set something up. If I'm standing next to a tree, both me and the tree are going to cast a shadow, okay? So there's two things that we're going to measure. So we could do the height of the person to the shadow of the person. And then we're going to compare it to the height of the tree over the shadow of the tree. Okay, you could also do it this way. I could go height of the person to the height of the tree equals the shadow of the person to the shadow of the tree. More than one way to set these up. Okay, and that's why I'm not necessarily looking for, did you set it up the right way? I mean, because there are wrong ways to set it up, but you just have to stay consistent. Height to shadow, height to shadow. Height of the person to the height of the tree equals shadow of the person to the shadow of the tree. There's more than one way to get there. Okay? So, in just a second,